Alright, so as I said a minute ago, the job now is to go back to the prime frame, the frame in which the pi meson is moving, and ask what happens there. And we already figured out the gamma factor for the prime frame with respect to the unprimed frame. We know that gamma is equal to E pi primed over M pi c squared. Okay, so now how do you get the energy of a photon in the frame where the pi meson is moving from the energy of the same photon in the frame where the pi meson is stationary? So for that you again need Lorentz transformations. We've already learned earlier in the course, at the beginning of the course, and again at the beginning of this revision lecture, that the time component of an event transforms like this: Ct prime equals gamma times Ct minus beta x. Okay, where Ct is the time component of an event and x is the position component of an event. And then the other Lorentz transformations look like this: x prime equals gamma times x minus beta Ct, and y prime equals y, and z prime equals z. As long as the velocity of the prime frame with respect to the unprimed frame is directed along the x-axis, this is true. Now, these Lorentz transformations can also be applied to momentum and energy. So you make the replacement: instead of writing Ct, you write E over c, and instead of writing x, you write px, the x component of momentum. So when you apply these two replacements to the Lorentz transformation for time, you discover that E primed over c equals gamma times E over c minus beta times the x component of the momentum. Right? So rearranging that a little bit so that the c isn't in such an awkward place, so multiply the whole equation by c, you get E prime equals gamma times E minus beta c px. Okay, so this equation gives us a way of figuring out the energy of something in a primed frame compared to the energy it had in an unprimed frame and the momentum it had in an unprimed frame. Okay, so in this case the thing we're talking about is the photon. We know what the photon energy is in the unprimed frame. That's the frame in which the pi meson was at rest. We calculated that E gamma equals m pi c squared upon 2. So we know what E gamma is, and we also know what c times p is, because I guess the momentum's a vector, so we have to talk about that now. So the point is that you can imagine that in some frame the pi meson is moving with respect to the observer. Now what we want to do is figure out first the maximum energy that the gamma ray could, or the decay photon could have. And that maximum energy is going to be the energy in which the Doppler shift is the biggest blue shift that it can be compared to the energy that it has at rest. And that biggest possible blue shift is when the observer is travelling in the opposite direction to the direction in which the photon's emitted. Okay? So biggest possible blue shift is when P gamma c, Px c equals minus E gamma. Right? That means that the momentum component is directed in the opposite direction. So the gamma these Lorentz transformations represent the case where the primed observer is moving in the plus x direction. So to maximise the energy of the photon we're talking about would be better to be moving in the minus x direction. Therefore the sign of its momentum is negative, and that's where this minus sign comes from. So if we substitute P gamma times c equals minus E gamma into the equation for E primed, we get E gamma primed equals gamma times E gamma plus beta E gamma. Now that's beginning to look like a tractable equation for the maximum energy of the gamma ray photon. Right? So let's do a little bit of algebra with that. Let's take that equation and write it at the top. So the things we know are that E gamma primed equals gamma times 1 plus beta, just factoring out the E gamma times E gamma. So E gamma we know, gamma we know, and the only thing we don't know is the 1 plus beta. So that's going to be more interesting. We can do a little bit of algebra, however, and show that there's a nice expression for 1 plus beta. So let me work that out next. Just keeping up with the things we have figured out. We know that gamma equals equals E gamma E pi primed, which is 100. This was 1 jet, right? You can't see that on the board. Gamma equals E pi primed over m pi c squared. We know that from before. Now we just need to figure out what 1 plus beta is. So let me show you a trick for doing that. We know that gamma equals 1 over the square root of 1 minus beta squared. Right. So that means that gamma squared equals 1 over 1 minus beta squared, or 1 minus beta squared equals 1 over gamma squared. Okay, so what I'm doing is trying to get an expression for beta by starting it as a function of gamma, which we already know. Okay, so that means that 1 minus 1 upon gamma squared equals beta squared, or beta equals the square root of 1 minus 1 upon gamma squared. Right? Now instead of plugging in gamma equals 7.63, a number, again I'm going to stick to my rules. It's best to have algebra rather than the numbers in your equations. So I'm just going to write that 1 upon gamma squared, looking up here, is m pi c squared over E pi primed. Alright, so this, here I get beta is the square root of 1 minus m pi c squared all squared over E pi prime squared. Okay, well that looks a little bit fierce, but let's not worry about it. Let's just keep calculating. And keep track of the things we know here. So E gamma primed equals gamma 1 plus beta E gamma. That's the thing we worked out earlier. It's another thing we know. And we're doing this calculation of beta. So inside the square root, I'm going to put everything over the common denominator of E pi primed squared. And in the numerator I get E pi prime squared minus m pi c squared all squared. But look at this, this is interesting, because remember that E pi prime squared equals p pi prime squared c squared plus m pi squared c to the fourth. That's the energy momentum mass relation, which means that p prime squared c squared equals E pi prime squared minus m pi squared c to the fourth, which is exactly what we have in this expression. So beta is actually equal to the square root of p pi prime squared c squared over e pi prime squared.